All right, let's dive into the invisible world of microchip design, because we're going to answer a really fascinating question. How do you test something that's almost impossibly complex? Well, the answer involves what you might call a virtual superpower.
Okay, so let's start with the central challenge here. I want you to imagine a machine, smaller than your fingernail, but with over 1 billion moving parts. We're talking transistors, all firing in perfect sync. I mean, how on earth do you even begin to make sure every single one of those parts works perfectly every single time?
And look, this is no exaggeration. Modern CPUs have billions, sometimes tens of billions of transistors. The stakes? They're just unbelievably high. A single microscopic bug in the design can cost millions of dollars in recalls and delay a product launch by years. Finding that one tiny bug in a sea of 1 billion, well, that's the massive headache verification engineers deal with every single day.
You know, this isn't just a matter of running more tests. With this level of complexity, the old, rigid ways of testing, where you'd write a specific test for a specific function, they just can't keep up. They're just too brittle. The second the design changes, they break. And you can't possibly write enough of them to cover every single scenario.
So, this whole problem forced a fundamental shift in thinking. The old way? It was like having a unique, hand-drawn blueprint for every single test you wanted to run. The new way is all about creating flexible, reusable templates that can adapt and generate countless unique tests all on their own. It's really about working smarter, not just harder.
And the solution, believe it or not, really boils down to one single incredibly powerful keyword from the System Verilog programming language: virtual. This one little word unlocks a whole set of tools that give us the flexibility and reusability we need to tackle that billion transistor problem.
Okay, so first up, we've got the virtual class. Now, in programming, a class is basically just a blueprint for creating objects. But a virtual class, that's a special kind of master blueprint. You literally can't build anything directly from it. The language just won't let you. Instead, you have to use it as a foundation that other, more specialized classes extend from, inheriting all its core functionality and then adding their own unique spin.
And hey, this isn't just some abstract theory. The entire industry-standard framework for chip testing, you might have heard of it, it's called the Universal Verification Methodology, or UVM. Well, it's built on this exact principle. The UVM is really just a library of powerful virtual classes that engineers take and extend to build their own custom test environments.
So, okay, what do these virtual classes actually let us do? Well, their first superpower is something called polymorphism. I know, it sounds complicated, but the idea behind it is actually super powerful and elegant.
So, polymorphism is just this: the ability for one command to behave differently depending on what it's acting on. Think about it like this. Imagine you have one key, but that one key can start your sedan, your sports car, and your truck. The action, turning the key, is always the same, but the result, the specific engine that roars to life, is different for each one. That's polymorphism in a nutshell.
Now, in the actual code, this difference is absolutely crucial. See, a standard, non-virtual method is rigid. Its behavior is locked in when the code is compiled, or at compile time. But a virtual method? It's flexible. Its behavior gets decided on the fly, while the program is actually running at runtime. This means a generic command can trigger a very specific, specialized action, which is what lets our tests adapt to whatever comes their way.
So, how does the code manage all this? It uses a process called casting. Upcasting is the easy one, and it's always safe. That's like taking your specific sports car object and just treating it like a generic car. No big deal. But the real power, that comes from downcasting. That's when you have a generic car handle, but you need to access the special spoiler on your sports car. You've got to do a safety check first to make sure it is a sports car before you try to use it. This lets your test bench handle generic things, but still get to their specific features when it needs to.
All right, so now we've got this smart, adaptable test code. That's great, but that brings up a new question. How does our software actually connect to or touch the silicon of the chip?
And it turns out there's a pretty big roadblock. You see, to make it reusable, test code is usually kept in this self-contained thing called a package. And there's a strict rule in System Verilog that says code inside a package cannot directly reference the hardware design. It's kind of like being locked in a sealed room and told you're not allowed to touch anything outside.
So, what's the solution? You guessed it, another virtual tool, the virtual interface. Think of it like a secure, managed portal.
It's a special kind of handle, or a pointer, that lives inside our test class, but it can be aimed at a real, physical hardware interface. It creates a bridge between that isolated test code and the physical chip design.
And making this bridge work is actually a pretty simple three-step process. First, you connect the physical interface to your chip design. We call that the device under test. Second, you declare a virtual interface, which is really just a placeholder inside your test class. And finally, you assign the real physical interface to that virtual handle. And just like that, boom, your test code has a direct line to actually wiggle the pins on the chip.
Okay, so we have all these individual pieces now, right? We've got virtual classes for templates, virtual methods for that cool polymorphic behavior, and virtual interfaces to connect everything. So how does this all come together in the real world?
Well, they all come together in the UVM, the Universal Verification Methodology. This thing is the industry-wide standard. It's the playbook that pretty much every company uses to verify their complex chips, and it is built from the ground up on these very virtual concepts we've just been talking about.
So, when you crack open the UVM toolkit, what you're really seeing is all of these virtual pieces working together in perfect harmony. It uses virtual classes as the reusable blueprints for all its components, like drivers and monitors. It absolutely relies on virtual methods to create those adaptable, polymorphic behaviors. And it uses virtual interfaces as that critical bridge connecting the intelligent test code to the actual hardware.
And at the end of the day, all these abstract software concepts have a very real, direct impact on our daily lives. The reason those insanely complex chips in our phones, our cars, and in all the data centers are so powerful and, thankfully, so reliable is because of this virtual verification toolkit. Which, of course, leaves us with one final thought. We've just seen how these virtual tools helped us conquer the billion transistor problem. But let's be real, chip complexity is not slowing down, not one bit. So as we're now moving into an era of trillions of transistors, with AI designing hardware, you have to wonder, what are the next virtual ideas? What new levels of abstraction will we need to invent just to make sure the technology of tomorrow actually works?